I bet you're ready for a new learning experience. Let me take you to the city of Intractability. Hop in! What is intractability? Before we delve into intractability, let us first know what is an efficient algorithm. The minimal requirement for an algorithm to be deemed as efficient is it must run in polynomial time. We can say that a problem is tractable if there is an efficient algorithm that solves it. Intractability is defined as the quality of being very difficult or impossible to control, manage, or solve. In computer science, intractable problems pertain to problems for which there exist no efficient algorithms to solve them. A decision problem is a problem whose output is a single Boolean value, yes or no. There are three classes of decision problems: P, NP, and co-NP. P is the set of decision problems that can be solved in polynomial time. In other words, these are the set of problems that can be solved quickly or in a reasonable amount of time. Having this quality would mean that these are tractable problems. Examples of polynomial time are big O of n squared, big O of n cubed, and big O of n log n. Examples of P problems are recognizing palindromes, divisibility of a number by another number. The other examples are sorting and matching symbols in a string. NP is a set of decision problems with the following property. If the answer is yes, then there is a proof of this fact that can be checked in polynomial time. In simpler terms, NP is the set of decision problems where we can verify a yes answer quickly if we have the solution in front of us. Examples of NP problems are knapsack problem, Sudoku, SAT, jigsaw puzzle, and Hamiltonian circuit. Solving a Sudoku puzzle will require some time and labor in order to scan and figure out the right numbers to fill in the missing numbers in each row and column. However, once the puzzle is solved, it will now be easy to verify if it is correct. Co-NP is the opposite of NP. If the answer to a problem in co-NP is no, then there is a proof of this fact that can be checked in polynomial time. NP hard are problems that are not known or proven to have solutions that are in polynomial time. An example of an NP-hard problem is a traveling salesman problem, which tries to find the shortest route between a set of points and locations that must be visited. To better understand the relationships, we have this diagram. Every decision problem in P is also an NP. An answer to a P problem can be checked by solving the problem from the beginning again. A P problem is also in co-NP. On the other hand, NP-complete problems are the set of problems which are both in NP and NP-hard. Intuitively, NP-complete problems are the hardest problems in NP. P versus NP is one of the long-standing problems in computer science that remained unsolved for years. It seeks to know that if a problem is easy to check for correctness, is it also easy to find solution to? P versus NP is one of the Millennium Prize problems, and anyone who could solve it will get $1 million. To explain it further, we have this diagram. P being equal to NP will mean that it is a problem that is easy to check and solve, or the problems that are checked in polynomial time can also be solved in polynomial time. Why do we bother to know if P is equal to NP? It is because if P does equal to NP, the world will change significantly. We would be able to solve problems like vehicle routing, plane ticket booking, circuit and database design, and have efficient facility locations. There would be a rapid development in the field of science and technology, engineering, health, and many more. According to an MIT complexity researcher, Scott Aronson, if P were equal to NP, then the world would be profoundly a different place than we usually assume it to be. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. Everyone who could appreciate a symphony would be Mozart. Everyone who could recognize a good investment strategy would be Warren Buffett. If P is equal to NP, there would also be downsides. The passwords that secures our bank accounts, emails, and personal information online will be at risk, since it relies on encryption, which is built on the idea of P not being equal to NP. People believe that P is not equal to NP, but no one has ever proven it yet. Hello everyone, we're here at the graph coloring street to get the things that we need. We will be discussing the graph coloring problem, particularly the vertex coloring, and we need to buy some coloring materials. Now that we have what we need, let's begin our discussion. What is the graph coloring problem, particularly vertex coloring? A proper vertex coloring of graph G is an assignment or labeling of colors to the vertices of G such that adjacent vertices are colored differently. Here, we have our example where there are 3 vertices. We can color the first vertex with blue, the second one with pink, and the last one with yellow. We can say that this is a proper vertex coloring because there are no 2 adjacent vertices that are of the same color. If we have n vertices in the graph, we can color it using n number of colors or less, which would also mean that each vertex have a different color from the rest of the vertices. However, what we aim here is to color the graph using the least number of colors possible. In this case, we can color the last vertex with blue since it is not adjacent to the vertex with the blue color. We can color this graph with 4 vertices using 3 colors. We will color the first vertex with pink, the second with yellow, the third with blue, and the last one with yellow. Notice that in the third vertex, we used another color because it is adjacent to both the first and the second vertex. A K coloring of graph G is a coloring of G using K colors. In this graph, G is 3 colorable. In this graph, G is 2 colorable. The goal of coloring the graph is to color the graph with the least number of colors. The chromatic number of graph G is the smallest number of colors needed to properly color G. It is denoted by chi of G. A graph G with chromatic number equal to K is called K-chromatic. In this graph, the smallest number of colors that can be used to properly color the graph is 3. So the chromatic number of this graph, chi of C5, is equal to 3, or we can say that it is 3 chromatic.